Now that we have defined a diameter and the possible number of diameters which can be drawn for the circle, let's see by taking into consideration two different diameters and see if the lengths are equal. This session is about investigating the lengths of the diameters for the given circle. Lengths of diameters. So let's see the lengths of diameters for the circle. Let me take a circle and let me consider two specific diameters for this circle. Now since I have the circle with center out here, let me draw two diameters passing through the center. Is what we get out here. So here I have a diameter AB which is passing through the center of circle, and I have another diameter CD also passing through the center. So there are two diameters AB and CD are the diameters for the given circle. Now as we take a ruler and measure the length of AB and then measure the length of CD, interestingly we come to the conclusion that they are same. Let's take another possible diameter which is in different angle, which is EF, and measure this diameter also with the ruler. We see that all the three lengths are equal. So here I see that by observation my AB length will be equal to my CD length, which is equal to EF length, which shows that any diameter taken with a circle will have the same length. Therefore, my learning outcome here is that all diameters for the given circle must be of equal length. Therefore, the conclusion: all the diameters for the given circle will have equal length, is how we understand the conclusion for the given diameters. So all the diameters for the given circle will have equal length. That's how we conclude for the diameters connected with the lengths. Length of AB equal to length of CD equal to length of EF. Now that we have discussed about length of diameter, let's also investigate for length of chord. What would be the length of chord? Will all the chords have same lengths? Just like all diameters for the circle have equal lengths. Let's investigate the same property for chord lengths. So length of chord. So let's take a circle and investigate the different sets of chords to see if all the lengths are equal. So let me take a circle. Now here, let me take two different set of chords or three different set of chords for the same circle. As we know that a chord is the line segment which joins any 2 points of the circle, so let me take a chord which joins these two line segments, which is A and B. Next, let me take another chord which connects this with this. Is how we understand. Let me take one more chord which joins these two lines. Of this. I find this chord to be very small. AB is the chord, CD is the chord, EF is the chord. And clearly I see that the length of CD is the highest, the length of EF is the smallest, and the next smallest is AB. So as we see these three chords for the circle, what strikes our mind is that all chords will not have equal length. Clearly, because if I take the points very near to the circle, then obviously the line segment joining them will have a smaller length. If I take 2 points very far away on the circle, then the line joining those 2 points will be a bigger length. So I make the learning outcome that with the chords, clearly chords AB, CD and EF for the given circle are not of equal lengths, as the reason being that the pair of points which we consider will decide the length of the chord. So ABC and this for the given circle are not of equal lengths. Therefore, I conclude all chords of the circle are not of equal lengths, is how I conclude for the circle. All chords of the circle are not of equal length. And also it's very important that the length of the chord is decided by the pair of points chosen on the circle. This pair chosen gives me a smaller length of the chord, and this pair chosen gives me the bigger length of the chord. So my learning outcome also is the length of the chord is decided by the respective points chosen for that circle. So here I have a learning outcome which is very important. Step. All chords of the circle are not of equal lengths. Also, the length of the chord is decided by the respective points chosen for that circle. These respective points chosen gives me the smallest length of the chord for the circle out here. These set of points chosen for the circle gives me the longest or the bigger length of the chord. And the highest chord is a chord which passes through the center of the circle, which is the diameter. So here the diameter will be the highest chord or the longest chord. So any chord which passes through center will be the longest chord and its length being the maximum. And therefore, we have also seen that the diameter is the longest chord in the circle. The diameter is the longest chord in the circle. Is how we just come to the conclusion. The diameter is the longest chord in the circle. Length of chords of the circle are not of equal lengths. Is how I conclude the session. Now that we have defined the various properties in a circle, most importantly the chord and the diameter, now comes how we connect the diameter with the basic definition of circle. I'm talking about the radius of the circle. So how do we connect the radius with the diameter? Is the biggest question in the session. So let's see this session about connecting the diameter with the radius of the circle. So let's see how the radius and diameter are connected for the circle. So in order for understanding these two combined together, let's take the circle into consideration. So here is a circle. Now for this circle, clearly I know that the radius is the line joining the fixed center to any point on the circle. So here I have this distance to be the radius. C is the center. Say my P is out here. So clearly I know that the line joining the fixed point to any point in the circle, that is CP, is the radius. And then let me extend this line to cut the circle on the other side. So here this line extends to cut the circle on the other side, say at Q. So this point is Q and this point is P. Now here I clearly understand that now CP is the radius and CQ also is the radius, because the other side of the circle, if I see, the line joining the center to any point in the circle is also the radius. So CP and CQ are the radii for the given circle. This part being the radius and this part being the radius. This also is the radius. Now, diameter. How did we define diameter in the previous session? A diameter is a chord which passes through center of circle. Now clearly when I see the line PQ, this seems to be a chord which passes through the center. Therefore, these two radius combine to form the diameter. Therefore, if I see the combined, PQ is the chord passing through center. Therefore, PQ is the diameter according to definition of the diameter. So the whole of PQ forms a diameter, as can be seen here. Also, it is very important to note that my PQ, which is taken out here, PQ is nothing but PC plus CQ. Because when this and this is joined, I get the bigger line. So PC plus CQ is PQ. So let me denote this radius with small r, and then my CQ and CP are equal. Therefore, this being r implies this also will be r. So my CQ also is r. And let me denote my diameter with d. So d is my diameter, r is my radius, which are equal, these two being of equal length. Therefore, each of them is r. So my PQ, which is d, is substituted for d in place of PQ. And then my PC or CP is clearly the radius, which is r. And again, my CQ, which is radius r, is substituted for CQ again for r, which on further simplification gives me d equals r plus r, which is 2r. So I find that there's a relation which connects the radius with the diameter, that is d equals 2r. That implies, how do you understand the statement d equals to 2r? D being the diameter and r being the radius connected with d equal to 2r implies the diameter of the circle is equal to twice the radius of the circle. So here I understand that diameter of the circle is twice the radius of the circle. Is how we understand the diameter connected with radius. Diameter is always 2r. That is, diameter of the circle is twice the radius of the circle. Two radius combine to form a diameter. Radius plus radius equal to diameter. D equals 2r. Diameter versus radius. Now that we have connected diameter with the radius, with diameter being equal to twice the radius of the circle, now comes the concept on understanding the arc of the circle. Today's session is about arc of a circle. So let's see the definition of arc of a circle. So let's consider a circle to understand its arc. So here is the circle with center out here. So what is an arc? As we see that the rim of the circle is this, so any part or piece of that rim which we find in the circle is called an arc. So as an arc is defined for a circle to be a part or piece of a circle, is how we understand arc. So for this circle, my arc is defined as the part or piece of a circle is called an arc. That's how we define an arc. So how do we define the part or piece of a circle? So imagine I take this part of the circle. So this part of the circle, let me darken up out here. So I have here a part of the circle which is arc. So if I take any 2 points in the circle, then that curved part of the circle between the endpoints is called an arc. Mathematically, an arc is defined to be the part or piece of a circle is defined as an arc. So there can be any 2 points taken on the circumference of the circle and we get any number of arcs. So arc connected with the circle. So in this case, AB is the arc. Note that for an arc, I use the symbol curve because a line segment AB is denoted by AB, which is called the line segment, and a curve deriving from A and B for the circle is denoted by AB, which is called an arc. So the symbol what I put on the top defines for this to be an arc and this to be a line segment. An arc always has a symbol this on its top. So AB is the arc for the circle as given here. The part or piece of a circle is called an arc. Is how we understand the arc. An example in real life is a pizza. When you take a pizza and cut the slice, we get the pizza with its piece, and the outer part of the pizza defines an arc. A piece of pizza connected with an arc. So outer face with endpoints taken as P and Q defines an arc. So PQ is an arc with its symbol. Is how we understand arc of a circle. A part or piece of a circle is an arc. Since there are different number of arcs, now that we have defined an arc to be a part or piece of a circle, let's see the possible number of arcs for a circle. This session is about investigating the possible number of arcs for a circle. So let's take a circle to investigate the possible number of arcs. Imagine I have a circle out here with its center. Now let me take a pizza cut in different shapes. Say I cut this out here, and I cut a bigger piece out here, and I cut totally 1, 2, 3, 4. So I have totally 4 pieces which are cut for the pizza. So I have the piece number 1, which is out here. And piece number 2, which is out here. And piece number 3, and then the piece number 4. So totally I have pizza number 1, 2, 3 and 4 pieces. So let's investigate each of the piece. So the first piece which I cut, let me take the endpoints AB, and for the second to be CD, and the third to be EF, and the fourth to be GH. Now each of the endpoints are taken for the pizza's pieces, with the first piece with endpoints AB, second piece with endpoints CD, and third piece with endpoints EF, and the fourth piece with endpoints GH. So I have totally 4 pieces of the pizza. So in this case, I see the length of this arc on the outer face is AB, CD, EF, and then here the length of arc is GH. So each of the arcs have different lengths, this being AB, CD, EF, and GH. So there are different possible lengths of arcs which can be identified in a circle. If I cut the pizza into 100 times, I get different number of pieces with different lengths of arcs. So my outcome here is that conclusion, there are infinitely many lengths of arcs for the given circle. There are infinitely many lengths of arcs for the given circle. Different arcs for different lengths of pizzas, different pieces of pizzas, is how we investigate that depending on the size of the pizza piece, the length arc changes. Bigger the pizza piece, bigger is its length of arc. Smaller the pizza piece, smaller is its length of arc. Is how we understand the length of arc and the possible number of arcs for a circle, with the conclusion that there are infinitely many lengths of arcs for the given circle. And all arcs are not of same length, they are of different sizes. So the lengths of arcs can be of different lengths, is how we conclude through the arc and the circle. Now that we have defined the arc and the possible number of arcs in a circle, we have come to the conclusion in the previous case of different pieces of the pizza that as the size of the pizza differs, the length of its arc differs. Therefore, we connect the previous concept with the session, which is major arc and minor arc. This session is about major and minor arcs for a circle. Minor and major arcs. So let's see the definition in brief. So let me take a circle in order to understand the 2 basic definitions for a circle. So let's see how we can understand the minor and major arc. Imagine I take this pizza and cut it into 2 pieces, such a way that I take the knife and cut it from the center of the pizza, slicing towards this. And I cut this, slicing towards this. Then when I remove this pizza out, I get 2 different sets of pizzas in this manner. So I get a pizza which is this, and I get another set of pizza which is So here I have two pieces of pizza which are obtained when I slice it in the center. Now as I see these two slices of pizza, what is that I observe is the biggest question out here. So clearly I see that this pizza has a very big length of the arc. This is also an arc, but these two arcs have a wide difference. That is, this is bigger in size and this is smaller in size. Therefore, any arc which is bigger in size is called major arc, and the arc which is smaller in size is called minor arc. So here comes which is called minor arc, and this which is called major arc, because this is bigger in size and this is smaller in size. So let's try to make the conclusion which says the arcs which make out the bigger and smaller. The longer arc of the circle is called major arc. And the smaller arc of the circle is called minor arc. So this is how we define the two basic arcs in the circle: the major arc and the minor arc. The longer arc of the circle is called major arc. The smaller arc of the circle is called minor arc. Is how we understand the relation between two arcs of the circle and major and minor arc. Major arc, the longer arc of the circle; minor arc, the smaller arc of the circle. Now that we have defined the major arc and the minor arc for the circle, now comes the discussion of a special case called the diameter. If I have a diameter for the circle, how do we try to take into consideration the arc connected with the diameter? Is what we're going to investigate in today's session. This session is about investigating the arc for the diameter of the circle. Diameter versus arc. In order that we understand the arc connected with the diameter of the circle, let's take a circle connected with the diameter. As we all know that a circle with the diameter just simply has a line passing through the center of the circle. I have a circle with the diameter. Suppose I have the diameter out here. Is how we connect. Now this circle assumed as a pizza, I would like to cut the pizza along the diameter. So I just try to cut the pizza in this diameter direction. So clearly I get two slices of the pizza. So here I get slice 1 and slice 2. So here is the first slice and here is the second slice. Now with these two slices of the pizza, I have the center which is common in this case. So what do we observe from the arc as obtained here and the arc which is obtained in the other piece of the pizza? So clearly I see that for this pizza, cut into two pieces, arc 1 is the arc obtained for the first pizza and arc 2 is the arc obtained for the second pizza, and clearly they are equal because this line exactly cuts the pizza into two equal pieces, and therefore we get two equal length of arcs, which makes us conclude that when we take the diameter into consideration, the lengths of arcs obtained by the diameter of the circle are always equal. That is, when I take the diameter, this arc length must be equal to this arc length, is how we conclude. So the arc lengths, the arcs obtained by the diameter of the circle, the arcs obtained by the diameter of the circle are always of equal lengths. So this is one of the investigation concluded that if the arcs obtained by the diameter of the circle are always of equal lengths. Is how I conclude the conclusion. Diameter makes the two arcs to be equal. So here arc 1 equals arc 2. Is how we conclude for two pieces of pizza. This defines two equal pizzas. Arc length of this pizza equal to arc length of this pizza. And also it's very important to note that this semicircle, when divided along the diameter, forms two semicircles. So this circle, when divided, forms semicircle 1 and semicircle 2. Is how we conclude the diameter connected with the arc. Now that we have discussed a special case of the diameter and the circle with its arc, a diameter defines equal lengths of arcs for a given circle, is what we have concluded. Now comes the discussion of semicircle. Let's see how a semicircle is defined through the diameter for the circle. Semicircle versus the circle. So the word semi itself says exactly half of the previous circle. So semi is half of the circle. Therefore, if I take a circle then half of it is a semicircle. So clearly when I pass through the diameter, the center lies out here. If I cut the circle along the diameter, I get a semicircle, is how I understand the semicircle. So here, this is a circle and this is a semicircle. For the circle and the semicircle, let's see the lengths of arcs, how the arcs are defined. So for this, I have two arcs which are formed along the diameter. This is arc 1 and this is arc 2, which are of equal lengths. So let me say the length of this arc is L. Then because the first arc is equal to the second arc in the diameter passing through the circle, therefore the length of arc being L also makes this to be L. And as we have seen, a semicircle is nothing but exactly half of the circle, so this length must be equal to this length. So clearly we see that each of the arc lengths are equal. Therefore, a semicircle is now defined in terms of the arc length. So let's see how we can define a semicircle for the given circle through its arc length. A semicircle is a part or piece of the circle whose arc length is exactly half of the circumference of that given circle is how we understand a semicircle. A semicircle is a part or piece of the circle whose arc length is exactly half of the circumference of the given circle. So if the circumference of this circle is say L or 2L, then the arc length of this semicircle will be L, because half of the total 2L is L. So given the circumference of the circle, a semicircle will have its arc length exactly half of the circumference of the circle, is how we understand the arc length connected with the semicircle for the given circle. Semicircle versus circle versus arc length. Now that we have defined the arc length for the circle, now comes the question of what would be the highest arc length of the circle as a special case. Today's session is about circumference of the circle connected with arc length. Circumference of a circle. So let's see what circumference is. Let's take a circle with certain center and certain radius. So here I have a circle, and for this circle I have the part or piece of the circle which is defined as an arc. So what if I don't cut the circle? A circle itself is said to be a part or piece of itself. So a circle itself is called a part or piece of itself. Therefore, the whole circle itself defines the arc, is how we understand in the general sense. So here we define the circumference to be the length of the complete circle is called circumference. So my circumference is defined as the length of the complete circle is called circumference of the circle, is how we define the circumference of the circle. So in this case, this whole of the length is called the circumference. Is how we define circumference of a circle. And interestingly, we see that for every arc length which are of different sizes, a circumference is the highest arc length for the given circle, or the longest arc length for the given circle. So my learning outcome here is that the circumference is the longest arc length for the given circle, or the maximum arc length for the given circle. Is how I understand the circumference connected with arc length for the given circle. The longest arc length for the circle is defined as the circumference for the complete circle. Now that we have discussed about circumference and arc lengths connected with circumference as a special case, now comes the new concept called segment. So let's see how geometrically a segment is defined for the given circle. This session is about segment of a circle. Segment of a circle. In order that we define segment of a circle, let's take a circle of suitable radius and center. Now, as we take the chord into the session, we know that a chord is a line segment joining any 2 points of the circle. So let me take the 2 line segments which join the chord to make the chord. So AB is the chord for the circle. Now clearly I see that when I make the chord in the circle, I always have 2 regions made by the circle. So when I just draw the chord for the circle, I have 2 regions made within the circle. Is how we get the different regions. So there are 2 regions made by the chord AB. So chord AB makes 2 regions within the circle. So this is region 1 and this is region 2. So these regions are called segments. The regions made by the chord within the circle are called segments. So now we define a segment to be the segments are the regions made by the chord within the circle. So segments are the regions made by the chord within the circle. So here the upper part is one segment and the lower part is one segment. So I have two segments for this. One is this and the other is this. So this is one segment which is defined for the circle, and this is one more segment as defined out here, with AB being the endpoints of the chord. So region 1 and region 2 are the two segments for the given circle. Segment are the regions made by the chord in the circle, and there are always two segments in the circle. Because a chord divides into two regions, there exist always two regions which are the segments for the circle. Now that we have defined segment of a circle to be the region as made by the chord within the circle, now clearly we have come across the conclusion that there are two regions formed by the chord of the circle. So here let's see in today's session about possible number of segments made by the chord in the circle. So possible number of segments for a circle. So today's session is about the possible number of segments for a circle. So let's take a circle for understanding the number of segments. So here is a circle, and let's take the chord. I have a chord AB out here. Then clearly I see that this chord is making two regions. Region 1 as denoted by dotted lines, dotted dots. And this is region 2 as given by slanting lines. So region 1 and region 2 are the two regions formed by this chord AB. So any chord of the circle always makes two regions, region 1 and region 2. Therefore, I conclude that for any chord of the circle which makes two regions within the circle, therefore, there always exist two segments for the circle. Is how we define the segment connected with number of segments. Since every chord makes two regions, within the circle, therefore every chord makes two segments. Therefore, possible number of segments for a circle is equal to 2. The number is 2. Therefore, number of segments made by the chord with the circle is equal to number 2. Is how I understand number of chords made by the chord number of segments made by the chord with the circle is equal to number 2. 2 segments for the circle, for any circle given in the branch of mathematics. Now that we have defined the segment and also explored the possible number of segments for the circle, now comes the question on what are those 2 segments called with specific names, and how do we define each of the segment or each of the region is what we're going to see in the session. Today's session is about major segment and minor segment. So let's see the basic definitions of major and minor segments. So let's classify the given circle into 2 different cases. Major segment and minor segment. As we all know that a segment is a region obtained when a chord intercepts the circle. So therefore, every circle makes 2 regions with the chord. Let's see which region would be called the major segment and which region would be called minor segment with its own specific definitions. So imagine I take a circle with the chord AB. Then clearly I find 2 regions in this chord. This is region 1, segment 1 and segment 2. But geometrically I identify that there is only one segment which has the center of the circle, but this does not have the center. So this has the center of the circle and this does not have the center of the circle. And this is how, with the property through which we classify the segments into major segments and minor segments. So let's first take the segment which has the center of the circle. So in this case, my first circle which has the center of the circle, and my second case of the segment which does not have the center of the circle. And then the segment which has center involved, the center of the circle involved, is called major segment, and the segment which does not have the center of the circle involved is called minor segment. So for this circle, this part is called minor segment and this part is called major segment because it has the center. So major segment is a segment which involves has center of circle in it, and here does not have center of circle in it, is how we understand the major segment and minor segment involved with the circle. The segment of the circle which has the center of the circle involved is called major segment, and the segment of the circle which does not have center of circle involved is called minor segment. Is how we define major and minor segments for the given circle. Now that we have discussed about major segment and minor segment, now let's connect the arcs, the major arcs and the minor arcs related with the major segment and the minor segment. This session is about connecting major and minor segments with their respective arcs. Major and minor segment connected with arcs. So let's see how the major and minor segments are connected with their respective arcs. For example, let's take a circle of suitable radius and center. So here I take a circle with the center out here. And here is the chord AB. Now I have the regions denoted with this. Now in this case, I have two regions, the first region and the second region. Now clearly we know that the region 1 has center, so this is called major segment. As discussed in the previous session, that major segment is the segment or the part of the circle which has center involved. Now because it has the center involved in this region, this dotted region is called major segment. Now this part of the circle does not involve the center, or there is no center of the circle in this region, so this is called minor segment. Is how we understand the major and minor segment. Now comes the question on how we connect them with the arcs. So let's revisit the definition of arc of a circle. We know that major arc is the arc which is bigger in size, and minor arc is the arc which is smaller in size. So obviously this acts as the minor arc, and this acts as the major arc. So what do we conclude from these two connections of the segments and arcs is that the length of the arc of the major segment or the major region is major arc, and the length of the arc of the minor segment or the minor region is called minor arc. Is how we understand the major and minor arcs connected with major segment and minor segment. So here the arc connected with major segment is called major arc, and the arc connected with minor segment is called minor arc. Is how we understand the relation between major arc and minor arc. The arc connected with major segment, that is the bigger segment, is major arc, and the arc connected with smaller segment, that is the minor segment, is minor arc. Connecting major and minor segments with major and minor arcs. Now that we have defined the segments and the arcs and the diameter and the radii, all the different connected properties of a circle, now let's see the new property or the concept called sector of a circle. Sector is today's session for the topics of circle. What is a sector? Let's define sector using the circle with suitable radius and center. So let's take a circle of suitable radius and this. Imagine this as a pizza, and I would like to define a sector through the real life model of a pizza. So let's consider a pizza which is cut exactly through the center. Say I cut this slice. So this is the piece of the pizza which I cut out there. And thus I obtain a piece of pizza out here. So this is the piece of the pizza through which I define a sector. Before that, let me take into consideration that this piece of pizza, as taken from the main circular pizza, has the center of the circle, has radius, has arc length. So a sector is a region which is enclosed between the two radii and the arc length. So a sector is now defined a sector is the region enclosed by the radii and the connected arc length. So this is said to be the connected arc length between A and B and O. So connected arc length between the two radii is between OA and OB, that is AB is the connected arc length. So sector is defined to be the region enclosed by the radii and the connected length of circle and the connected arc length is how we define the sector for the given circle. A pizza cut with a piece of pizza has the center, has the radii, has the arc length, and a sector is the region enclosed by the radii of circle and the connected arc length is how we understand a sector in terms of the arc length. Sector with its definition. Is how we define a sector of a circle, part of a circle, a piece of a pizza for a given Domino's pizza. Now that we have defined a sector, now comes the question on what are the different types of sectors which exist for a given circle. This session is about the types of sectors of the given circle. the types of sectors for a given circle. Just like we had the different definitions for an arc, we had major arc and minor arc. Even for segments, we had the classification of segments into two types, major segment and minor segment. Similarly, we classify sectors into two forms, of course, major sector and minor sector. So let's see the definitions in brief. So the sectors are classified into two types. One is major sector and the other is minor sector. So how do we define major and minor sectors is the biggest question out here. So in order for that, let's take the circle into existence. So let's take a circle out here with the center fixed and with suitable radius. Let me cut this pizza assumed to be a circle into a piece. So I cut the piece of pizza out here, and one of the slice is this and the other slice is this. So I have two slices of the pizza. One is this and the other is this. So what is the difference between these two slices is what defines the two types of sectors. Now as we know that the circle defines two sectors, one is this and the other one is this. So there are two types of sectors identified here. One is this and the other is this. So here let me take the two possible sectors with the first piece of pizza which is taken out here, is out here, and the second set of pizza which is taken in this case, which is like this. Out here. Obviously this slice of the pizza is bigger in size and this slice of the pizza is smaller in size. Therefore, we call this as major sector and this as minor sector. Mathematically, a major sector is a sector which involves major arc. So this sector has major arc and this sector has minor arc. So therefore, a sector which has major arc involved is called major sector. A sector which has minor arc involved is called minor sector. Major sector is the sector which involves major arc for the given circle. Minor sector is the sector which involves minor arc for the circle, and hence the smaller piece of the pizza is called minor sector and the major piece of the pizza is called major sector. Is how we define the two types of sectors classified in the branch of circles, major sector and minor sector. Now that we have defined the sectors into consideration and the different types of segments taken into consideration, let's take the special case of the segments, the maximum possible segment or two equal segments taken in a circle. Connecting the segment through the diameter is what we are going to discuss in the session. Segment through the diameter is the session about. through the diameter. Let's take this as a special case where the segment is through the diameter. We have defined a segment to be a part of the circle when the chord is taken into consideration. That is, when I take a circle and the chord, the two regions are called the segments of the circle. Now let's take the possibility of what if the chord passes through center? What if the diameter is taken into consideration? So let's take a circle in defining a segment through the diameter as a special case. So here I have a circle where I have the center out here. So imagine my chord here is the diameter itself. So this diameter also forms two regions out here. The region 1 and region 2. So I have two regions, region 1 and region 2, formed by the diameter. And interestingly, we also note that the two regions as formed by the diameter AB are equal because they are exactly through the center. Area of region 1 is equal to area of region 2 because AB is the diameter. It exactly divides the circle into two equal parts. Therefore, I conclude that the two segments are equal. The segments as made by the diameter of a circle are equal in area. Therefore, the segments as made by the diameter of the circle are equal in area. That is, area of the region 1 is equal to area of region 2. Is how we understand the segments when passing connected with the diameter AB. The segments as made by the diameter of a circle are equal in area, and hence the major segment and minor segments are equal. And also, when I take each of the segments, I get a semicircle. Is how I understand each of them being a semicircle. So when segments are divided along the diameter, they form two different semicircles, and therefore also the two segments as formed are called semicircles for the given circle, because this is the other way of defining a semicircle through the segment definition. The segments as made by the diameter of a circle are equal in area. Also, the two segments as formed, region 1 and region 2, are called semicircles for the given circle. This region is called the semicircle 1 and this region 2 is called semicircle 2. The two segments, when formed through the diameter of the circle, will form two semicircles, is what I make as the learning outcome. Semicircle connected with segments through the diameter as a special case.